Not many ideas have shook existing paradigms in the same way as quantum mechanics. The theory's development in the early 20th century changed the way physicists thought about the universe of particles so radically, it led Danish physicist Niels Bohr to state, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." You see, quantum mechanics is unlike any other physical theory in that it introduces an uncertainty or limit on how much we can possibly know about particles. At best, we can deal with probabilities arising from the wave function. It also introduces an unusual example of the observer effect, a phenomenon that has been misunderstood countless times as consciousness having a direct effect on observed reality. Wait, but what exactly is the wave function? The function, denoted by the Greek letter psi, can be understood as an expression for the amplitude of a particle wave. The amplitude may have no physical significance, but psi squared has important physical consequences. It can be used to find the probability of a particle at a given point. The sheer confusion that arose from quantum theory led to various interpretations as to what exactly is happening in the world of particles. The most popular of these interpretations is the Copenhagen interpretation, devised mostly by Niels Bohr, remember him, and Werner Heisenberg in the 1920s. The Copenhagen interpretation, in its essence, tells us that a particle can exist in a superposition of states. The act of observation causes the particle's wave function to collapse, and the particle assumes a specific state when a measurement is made. To understand the Copenhagen interpretation, let's take a look at Schrödinger's famous thought experiment, Schrödinger's cat. Imagine we have a cat in a sealed box with some radioactive substance that has an equal probability of decaying and not decaying in some unit of time, let's say an hour. We also have a Geiger counter connected to a hammer via relay, which will in turn smash a tiny bottle of poison if the radioactive substance decays, causing a very painful death for our poor cat. Before someone opens the box and checks the fate of the cat can be thought of as being in a superstate of both dead and alive. The interpretation rests on two major features of quantum theory: Heisenberg's uncertainty principle and Bohr's principle of complementarity. The uncertainty principle is summarized by a simple uncertainty relating the standard deviation of the particle's position and its momentum, while stating that product of both can be no greater than some multiple of Planck's constant. Physically, this can be understood as the more one knows about a particle's position, the less they can know about its momentum, and vice versa. The principle of complementarity simply states that particles possess certain properties that arise in pairs, such as a wave, particle duality, and momentum position.